Well, welcome back, everyone. We're just kind of running the clock before we get started. About 20 more seconds. Well, it's official. We can begin. Welcome back, folks. So we're clear of the 25% mark. We're now on week number 5. And I don't have a ton of announcements. It's just an ordinary week we're getting through. But first announcement is homework number 3. We gave a blanket extension to the entire class. So it's officially due today. And I'll probably get in the habit of making that kind of an extension. The issue with the homework assignment number 3 was if you're working really hard on studying for the exam and maybe you notice 3.1 wasn't even on the list of sections that's on the exam, it's kind of natural to focus on just studying and get to the homework right after. So whenever we have a actual exam week, I'll usually give that kind of extension on the assignment that would have been done the Thursday of that exam week. Then our next section that's coming up due is assignment 4. This one's really very short because of that interruption last Thursday. So just this section here. I would say think of this as kind of an opportunity to catch our breath, get caught up, as we start working towards our next upcoming assignments. So assignment 5 is now just getting built up. Any questions about that so far? Okay, let me hide this for just a moment so it's out of the way. I think we're just about ready to get started, folks. I did make a note here. Let me bring that back. We're on section 3.3, so we're going to be treating the derivatives of the trigonometric functions. And because trigonometry, it could have been a while since you've seen those, we'll try to bake in a review into our lesson as we go through those topics. If you want a really, really good review of trigonometry, your appendix in the back of your textbook is excellent. It gives you everything you would want to know as a student in calculus about trigonometry, everything you need to get through. I put this right here, my just basic notes on trigonometry. It's an even condenser version of that. Also, our sections that we're going to get through in this week do have some tricky ones, and I always mention when I feel like, for me, these are some personally tricky sections. There'll be another one coming up in chapter 3. And the reason for saying this is not to scare anybody away, but mainly anything you do to pre-read that section before the day of the class will help out tremendously, especially for certain sections like these two right here. So that's my announcement so far. And pretty much the Moodle website is just going to keep repeating and repeating over and over. Don't forget that you can always, if you miss a class, dive into the recorded lectures. That's where all the playlists are for every lesson we've done. If you need blank lecture notes as Word documents, maybe that just works better with how you take notes. They're always available here. And all these sections, they get updated with the actual solutions. If one of them's blank, I probably just forgot to upload it. So you're always welcome to say, hey, Mike, could you upload the notes? And I'll get onto it right away. So last thing that's coming up. So we scroll through here, we have our, let's see, midterm week and exam number 2. There's nothing fancy about midterm week for this course. It's just an opportunity to say what's your grade on midterms. So exam 2, it's going to be the same kind of deal. So that's where we're at, where we're headed. Any questions at all, folks, before we get started? Okay, well, let's dive right into the wonderful world of trigonometric functions. First thing we have here is what was put on exam 1? And it really didn't have a huge amount of purpose on exam 1, but I mainly included it just to have a page for scratch. And also as a reminder on every one of my exams, including the final exam, I'm going to put this trigonometric table on your exam. You might have to use it in exam setting. And even if you have calculators, it's still useful because occasionally we have to give an exact answer in an exam setting itself. So let's start off by just practicing trigonometric functions based off this table here. Trigonometric functions are wild in that they're defined in the weirdest kind of way. We start with a geometric object, like this unit circle right here. Given an equation, that equation for this black line where the arrow is pointing is x squared plus y squared. Because we said it's a unit circle, the radius is 1, and that has a value 1 right there. Now in section 3.11, we're going to put a minus there, and we'll call those hyperbolic functions. It's a new kind of trigonometry which we can run through if we just change the geometry of the shape we're basing our functions off of. So really pretty weird, kind of wild. But once you have the unit circle down and these radian or degree measurements, we can now start defining things. For example, we can say sine of a radian measure theta. Say, for example, when we say theta, we mean something like this. We start at the positive x-axis. This would be the initial side of the angle. Rotate to say here, that'd be the terminal side. And then in that case, sine theta, theta would have been the 60 degrees itself. But the way it's defined is purely in terms of the coordinates. Sine theta, anyone happen to know which coordinate this would be? The x coordinate or the y coordinate? Good call, this one's y coordinate. And so if we want to say let's put our just practice problems over here. If we want to do maybe sine of, maybe it's pi over 6. We go find pi over 6, our rotation's that far. Grab the second coordinate, 1/2, that's our y coordinate, and our work is done. We have a 1/2 there. So not so bad. Likewise, cosine theta equals x. And when we go to the tangent function, we could call this y over x. Nothing wrong with that. That's how it really is defined. But I think for the purposes of our class, it's better to think of tangent theta as being sine theta divided by cosine theta. So that's our first column of functions. We go off to the next column and take the reciprocals of all those. So next is the cosecant function. So I'll call that cosecant of theta. It's 1 over sine theta. And that's what we mean by the reciprocals. If we take the reciprocal of sine, so it's 1 over sine, we're just getting cosecant out. Go down a row, cosine is associated with secant. So secant of theta is 1 over cosine theta. And lastly, cotangent theta. There's a lot of ways to write cotangent theta. You could call it x over y. You could call it 1 over tangent theta. Or we could call it cosine theta divided by sine theta. I'll go with that last approach. Cotangent is cosine theta. Let's make that look like theta first. There we go. Divide by sine of theta. So that's the whole spiel. That's all 6 trigonometric functions. And at the moment, we haven't done a speck of calculus, right? This is all just kind of review so far. I'll leave it up to the class. Should we do another evaluation like this one here, just for review? Or how do folks feel about this? Not so bad? Some say not too bad, that's awesome to hear. Okay, we'll do a couple evaluations of these as we go through the notes today, so we'll have opportunity to practice. And each time we do one of these evaluations, I'll jot down something like this real fast to just show you how I calculated it. So you can imagine if this was an exam, you would have just gone to this table, grab the values, or if you have it completely memorized pat, then good on you. That's the better place to be, I'd say. So next thing that's going to happen is we need to know how to take the derivatives of all 6 of these functions. But before we jump into that, let me go to the actual optional notes right here. Anything that's called review material, it's not required that you jump into that. But if we go in here, I just want to show you kind of how it's organized. This is really how you would start defining the trigonometric functions. You'd have to know what radian measure is, all that great stuff. We just put down this definition of the 6 trig functions. We'll be using these right here. And then if we keep on scrolling down, there's lots of crazy and scary identities. I would never write an exam question that needed something like this out of the blue. So that's something you can rely on. Occasionally a homework problem might need something from this list. So if you're stuck on a problem, email me or take a look at this for some inspiration. It might get you through the problem. Well, let's keep on scrolling through here to see what we're getting into. Finally, this is the major thing we want to take a look at. Our theorem tells us when our author has a couple approaches, one's geometric, and she also gives definition proof using the definition of the derivative. But it goes like this. The derivative of sine must be cosine. Likewise, the derivative of cosine becomes negative sine. And here's how it's kind of indicated that it should be that way. This is not a proof, but it's a good way to think about it. If this is the sine function, then what our author has done is went to every single spot where there'd be a horizontal tangent line. That's what those red bars are. At a horizontal tangent line, the derivative results in a zero. So the graph of the derivative should be right across the x-axis like you see here. So everywhere that sine had a local maximum, like right here, or a minimum, say right here, we have the graph below for the derivative crossing the x-axis. Doesn't tell us cosine is exactly the right function, but it makes it absolutely plausible that it's probably a good place to start looking. So that's our first big theorem. Derivative of sine is cosine. Derivative of cosine is negative sine. Any questions, folks, about that at the moment? Okay. If you're a little bit more curious about this, oh, sorry, go ahead.
So sine of x is just y.
Well, in this case, if we say sine x, we're saying the measurement right here is a measurement amount of by x instead of theta instead. Let me try to see if I can say that better. If you see an x here instead of theta, it means the actual rotation was by x amount like this. And honestly, it's a great question because trigonometry is defined in terms of theta, and you would normally put theta here. The reason x is finally coming or suddenly coming into the picture is when you go to actually graph the functions, like say sine x or cosine x, you want to do it on the xy plane. And so x and y now have a different meaning in this case here. Does that help out with those ideas so far? Gotcha. So again, that's a really confusing and interesting point with trigonometric functions. If you see an x here and a y here, it's just because we're plotting them. But if you're going to the original core definitions of the trig functions, you'll often see a theta, that's this rotation. Put that in the notes officially. And then this x and this y have a different meaning in this case. It's going back to those coordinates right there. But other questions at the moment? Okay, again, trigonometric functions are weird because it's a function defined off of a geometric object like this. So a really common question is, well, you could say sine of a measurement theta is y, or you can graph it and say sine x, if you're at say pi over 2, you get the value of 1. But the question people would really want is, what is the formula for sine x really? And here it is. It's not the friendliest formula, but that's the real thing. It won't be part of the course. It comes out of page 762 of your actual textbook. I put this on our notes here just because if you want a function written out as an equation, it has to look like this for both sine and cosine. Notice the ... That means these terms carry on forever, unstopping. But if you did take the derivative of this sine function, let's do it right here. You'd say d by dx sine x. First thing you differentiate is this x. That would just turn into a 1. When you differentiate the x cubed, let me do this in the margin. 3 would come down. Power of x would be 2. There's a 3 factorial down below, but that just means 3 times 2 times 1. To get 3 times 2. And so this would become x squared over 2, or x squared over 2 factorial. 2 factorial is 2 times 1, still 2. So when we differentiate this term, now there's 2 arrows on it, we get plus, excuse me, there's a minus sign ahead of it, x squared over 2 factorial. And that pattern continues. Differentiate this one, you get plus. The 5 would come down, canceling with the 5 factorial, and you get x power 4, divide by 4 factorial, and so on forever without repeat. Or excuse me, yes, without ever repeating, definitely not ending. So that's a pattern if you differentiate sine x. Yeah, go ahead. It is the Taylor series, exactly. It'd be considered the Taylor series for sine and cosine. That's the only way to get a nice closed form formula for both of those odd functions without having to draw a circle and say it's this coordinate or that coordinate. So if you keep on differentiating these, notice what you're getting is derivative of sine, 1 minus x squared over 2 factorial plus x4 over 4 factorial. It's exactly that. Again, this isn't a proof. It's actually kind of cheating a little because we went to the Taylor series, like you said, for both sine and cosine. That's another way to say, yeah, it's plausible. Derivative of sine is cosine. Do the same game with cosine. Differentiate that, and you get negative sine. So that's kind of what's going on with the trig functions. Any questions at all, folks, with these notes at the moment? Okay, again, this is not something you have to memorize for class right here, just a demonstration, much like the graph is right here. The biggest takeaway so far is this theorem that's restated right here. The derivative of the sine function comes out as cosine, and derivative of cosine becomes negative sine. And that seems kind of grim at the moment when you think about it, because there's 6 derivatives we need to discuss. And my theorem down below only does sine and cosine, and there's 4 more functions to handle. But here's how we could say differentiate something else. One nice trick about trigonometry is if you have information on sine and cosine, you pretty much have information on all of these other 4 trigonometric functions because they're defined in terms of sine and cosine. So example 1 looks a little bit weird, but what we're going to do right away is prove that formula right here. We want the derivative with respect to x of cosecant theta equals negative cosecant theta tangent theta. I notice there is a typo on this. Let me see if I can fix it real quick for us. That should have said theta right there. Sorry for that weird little typo. Without a theta in that position, if you're differentiating cosecant theta, and theta is the independent variable, this would not have made sense without that theta right there. Or we could have called it cosecant prime. So let's write it out like this. Cosecant theta prime, if you decide to go with the prime notation, it's a little bit safer because you have to be very specific with Leibniz to make it appropriate. Sorry for that typo there again. So we're differentiating cosecant theta, but here's the major trick. Recall that cosecant theta is just 1 over sine theta. So we can rewrite the problem this way. We want the derivative of the reciprocal of sine. The moment we do that, we now have a different kind of conundrum. There's 2 functions. There's the constant function, which always is going to give back 1 in the numerator, so it's harmless. But there's the not constant function in the denominator, sine theta. That means we need to use the quotient rule on this thing. There's no great tricks at this spot of the chapter 3 to get out of quotient rule so far. So here's our setup and a reminder of how quotient rule goes. Sorry, say again. Oh, good call. There's going to be a minus in between up in the numerator. Then a couple sets of parentheses. And don't forget the prime symbol. We're differentiating on the first one here and on the first one here. Then the denominator's to the power 2, and we're just filling in the blanks from here on out. Let me get these colors going. So for the numerator of 1, we'll put a 1 here. We'll differentiate it later, 1 here. Then sine theta goes in all the empty locations. So that's our start so far. Any questions at the moment, folks, with putting down the quotient rule on this thing? Okay, if we're happy with this, we'll go to that location. It's asking for us for the derivative of 1. What will we get back from that portion? Exactly. So that whole thing is really just wiped out, basically, right? It's just gone once we're asking for that derivative. For the sake of the notes, I'll write out this way. 0 times the sine theta minus. Oh, I do seem to have a problem here. My prime symbol, let me fix it, should have been right here. Let me highlight these just to make sure they're a little bit more readable. You should slow down with these kinds of things. The quotient rule should differentiate 1 and then the other, not both at the same time. We were going to get a wild result. Here, we'll just have the constant 1 multiplying, so nothing happens. This is saying derivative of sine theta, and there it is. We get a cosine right out of that. So this will be cosine theta. And if the problem did have x's, I would have wrote cosine x like is indicated up here in the formula as well. So with that one down, only thing that happens in the denominator is we get sine squared theta. So the answer is negative cosine theta divided by sine squared theta. But that's problematic, right? Because we also said we're trying to prove this formula. The answer needs to come out as negative cosecant theta times a tangent theta. So now we have to do just a little bit of rearrangement on what we see here to try to get to that result. It's not as if anything is wrong with this as an answer, but with calculus, if you had to use this as your derivative, more often than not, that'd be more complicated to work with as versus this one right here. So we're trying to get to that slightly more simplified form. Because it says negative cosecant, we can go down here and just split off our signs in the denominator. It could be negative 1 over sine theta, multiplying a sine theta times cosine theta. No worries. So pretty much all I've done is I've taken the negative 1 over sine theta out and left the cosine 1 factor of sine theta right here. But this is really good for us because, like we said, 1 over sine theta, that is a cosecant. We just need to copy that negative sign. So we have negative cosecant of theta. Lastly, cosine over a sine, that one turns into a cotangent. So cotangent theta. Double checking, we're trying to get to here, negative cosecant theta, cotangent theta, and that's exactly where it falls. We just had to use the quotient rule. Oh geez, what did I do? Sorry, I clicked on something and it changed. We just had to use the quotient rule and simplify. Yeah, go ahead.
Yeah, negative 1 over sine theta again.
When we multiply from here to here across the denominators, it gives me the sine squared down below. Then multiplying across the top, I would just get negative 1 times cosine, so the negative cosine in the numerator. So kind of like reversing fraction multiplication, just to separate out 1 over sine theta, pretty much. Does that make sense there? Awesome. Yeah, go ahead. Oh, sorry, I'll get right back to you also. Negative cosecant theta, tangent theta. You know what? That might be a typo in the notes as well. Let me double check my. Right. But I'm looking down at my notes. I think I have a typo there too. I think it should have been cotangent. Sorry about the confusion on that. So right up here, I think I would have lost some points on this as an exam problem for sure. But I should have said, prove that. Geez, that's a second typo. Should have said theta, no negative cosecant theta, and let me put here a little correction. Cotangent theta. Sorry for that right there. I even highlighted it and felt good about it. And now it finally matches up with that correction. Question over here?
No.
Gotcha. Thanks for alerting me, folks. That's a nasty typo to leak through the notes. I better make a really quick correction. Fix 3.3. I'm pretty sure I'll remember what that means if I take a look at that note. Phew, well, we got through it, folks. There is 3 more to go through, but we can't do this all day, right? We would never get through all the derivatives. So the next table is like our official table. But first, any questions on this derivation that we read through? Okay, thanks again for spotting those errors, folks. That's kind of frustrating to get through first time looking at this. But looking at the table, let's double check. That's exactly how it should be. So this is the biggest takeaway of the notes, pretty much. Let me see if I can make this bigger just for emphasis. The derivatives of all 6 trigonometric functions, first 2 were supplied. We showed this one after 2 corrections. Sorry again about that. And if we want to prove any one of these other ones, it's really the same process as what we saw in example 1. It's a lot to memorize. There's 6 derivatives here, and they have strange patterns on how they get together. But here's the danger. The exams are open notes, and so you could just put this on your note card, your page of notes. In fact, I would say that's a really, really good idea. But if you have to look up a derivative like one of these each and every time you calculate, say in calculus 2, calculus 3 as well, other classes, it's easy to get kind of bogged down. So one thing I would say is a really, really good strategy, let's put it here, would be to memorize this entire table some way, somehow. You can make flashcards, try to fill these in cold just to refresh yourself on the definitions. If you have this down pat, it's going to make everything else you do involving trigonometric derivatives much, much faster and easy to get through. So I'll put here. Memorize once I recall how to spell this, mem or this table. Not because you have to, just a very good idea, I'd say. Now, when you look at this table, there is different things going on. I always go sine, cosine, tangent, and the reciprocals on the right, just to organize, but it's also for calculus. Interesting things happen in this table if you have it organized just right. The first thing that pops out is those negative signs. They emerge in just these exact locations when you take these derivatives. And in fact, if you look a little closer, you get a negative every time you take the derivative of a cofunction. If it's an ordinary function like sine, you just get cosine back. Derivative of tangent gives you secant squared back. And derivative of secant becomes secant times tangent. But like we saw, when you differentiate a cofunction, we did this one from scratch, you will get a negative sign. So matching up the negative signs is not so bad if you memorize that trick there. And there's other weird things that happens on this table. For example, if you take the derivative of a secant, you get secant times tangent. That's kind of odd. It's kind of like differentiating e to the x and getting an e to the x back. Except if you differentiate secant, you get secant back times tangent. Likewise, if you differentiate cosecant, you get cosecant and cotangent, along with an extra negative sign as well to cinch the deal. But I'll leave the highlighting to here so it doesn't get too busy. And our goal is just to practice with these derivatives right here. Any questions at the moment so far, folks? Okay, when we go to practice these, we're probably going to be using these formulas right here at some point. So let me just take this. I'll paste it into the notes so we can more easily reference it whenever we have to use it. And here's our first problem to start us off then. So all we're doing is just calculating a derivative. And for part A, this one is going to be f of x equals 2 cosecant of x plus secant x. Now, you don't have to put the parentheses around the of x in the function notation like I'm doing here, but if it helps you to see how one function is going into another or something along those lines, it's not a bad strategy. If you write your answers like this, secant x, tangent x without parentheses, that's okay too. So that's our thing to differentiate. And with our table right above, it's really not too bad. We just have to be careful as we go. So below, we'll call it the derivative. So either df dx, or I'll go with f prime this time. When we go to use our rules, everything we've done from 3.1, 3.2, and now 3.3, they all combine together. And where the red dot is, because 2 is multiplying, it's the constant multiple rule. Just no change on that 2. When we differentiate cosecant, we're just bringing in this information. So I'll write here, just to be careful on how things go together. There's the 2 unaffected. Derivative of cosecant becomes negative cosecant of x times cotangent of x. Then we're pretty much done with that. We go over here to the plus and differentiate secant. Derivative of secant is just as weird as cotangent. We get secant and tangent x back. So honestly, the cosecant, cotangent, they're the weird ones to me. Yeah, go ahead. Oh yeah, absolutely. Didn't match up my delimiters too well there. Thanks for spotting that. The next derivative of secant becomes the secant x times tangent x. So here's secant x times tangent x. At this stage, we're pretty much all set. I mean, there's not much simplifying to do here. If you left it just in this format, I'd say that's an acceptable answer. There's no reason to try to combine terms, try to re-express this and simplify it, unless we had cause to do so. For me, for my own sanity, I probably would take one step and just call this equals -2 cosecant x cotangent x plus secant x tangent x. Just to multiply these and put them together is probably all I would do to it at that stage. We did it, folks. That's our first bona fide derivative. pretty much the homework questions are going to look about like this here. Any questions at all, folks, on getting through this one? Okay, let's try this again. So this next one is now different. B goes G of t. So now the input is t. That's kind of weird, but we'll get through that. Will be a cube root of t multiplying sine t. And let me just put a line here, separate these problems. So for this new problem here, well, it's not like the 2 cosecant x. We didn't use a product rule on that. We used the constant multiple rule. But this is finally a bona fide product rule. So we have to be really careful with this one. So when we get started here, we'll just say, after we get some space, G prime at t. And actually, let me change my color just a little bit. I'll write it down here. And I'll organize it in this kind of way. So if we're using the product rule, we have to have a notion of what function is what. So the first one will be in blue, second one in green. Throw down 2 pairs of parentheses separated across, this time addition, because we're using product rule. Let me try to get those primes right. We'll differentiate the first function here and second function here. So that's our product rule. Now, all we need to do is carry this inside. But if we put cube root of t inside here, honestly, that does stump me. I usually want to do some work on the exponent. Anyone see what the exponent ought to be, just to make it cleaner to work with? Exactly, power 1/3 is just way, way easier to work with. So if you get your bases always in the numerator and your exponents always written as actual exponents, not radical signs like this, then all we're using is the power rule, this one right here. The derivative with respect to x of x power n is n times x power n minus 1. And that's exactly in the format we want it to be in order to use that power rule right here from 3(1). So we'll use t power 1/3. We'll go here and here. Last is sine t. Then from here on out, we just get to differentiating. So now we're going to crank it out. This is not too bad to start. No matter what the exponent is, it becomes a coefficient. So it's 1/3 multiplying t to the new power of, just subtract 1, no matter what the situation is. So visualize 1/3 minus 3/3 to get a new exponent of negative 2/3. That portion's done. When we go here, nothing much happens, so we just carry down sine t. Copy here as well, t power 1/3. Then here, we do have to take a derivative. I've scrolled a bit off that table, but anyone recall the derivative of sine? Good call, we get just a cosine t. Then, just like on part A, where the problem ends, I don't really see what I could do with that. You could change the exponent by bringing base t down to the denominator, but that's more of a stylistic choice. It's not required. I don't see anything to factor, nothing cancels, so it just ends right at this stage. That's part B. Let me put a line there. So we did it, folks. That's another pretty fast derivative. Now that we have a pretty good machinery for products, constant multiples, really, although this is new, it's pretty quick to get through once we have the right table or the right stuff to work with. Any questions at all, folks, with those first 2 problems? Okay, let's try out something that starts to get a little bit weirder. So for part C, in part C, I have, let me move this over, an f of theta. It's not an independent variable. Well, it's not x anymore. That's kind of a comfortable place to be in. We went to t. Oftentimes that might mean you're doing an applied problem and t represents time. Now we're back to theta. So if we're using theta, then f of theta should be defined in terms of cosine. And now we have to say cosine of theta to make the formula correct here, times 1 plus secant of theta. So that's our thing to calculate. And as you look at this, that is a product rule, right? We have one function cosine multiplying another function, 1 plus secant theta. But this is a case where you absolutely would not want to do the product rule on this at all. Sometimes the trigonometric functions simplify, and when they do, they could simplify massively. So your derivative is really not the product rule at all. So probably the best advice I would give for this section is always look before you leap. You're saying it's going to be 1 plus secant squared? Are you saying, oh, I see you're meaning one of these right here? Almost, not necessarily though, but that's a good call. You'd always want to know how these are going to come into play, and I have a problem coming up that's about to use it. But this one's a little bit different. The issue is, if you see a cosine theta and a secant theta, you might want to recall that. Let's go up here. Exactly. So our cosine, if that's x and secant is 1 over cosine, when you multiply those together, it's just cosine over cosine for an immediate cancellation. So in other words, cosine theta multiplying secant theta, it's nothing but cosine theta multiplying 1 over cosine theta, which means you get a 1 immediately for an automatic cancellation. That's another reason to kind of keep this table in that sort of organization. If one column multiplies across the other column, you always get a 1 each and every time. So coming back down here, let's make those distributions happen and say that f of theta is going to be from here to here, that's just a cosine theta. But when we multiply here to here, cosine times secant just becomes a 1. So this is plus 1. So now with that one operation, it's still not the derivative, but the derivative is essentially immediate. Would you folks agree? Whereas if you differentiate this without changing it at all, you have to run through a product rule. It'll take some time, and it might actually take a while to simplify it down to the point of what's going to happen to our derivative. For us, we'll just write f prime of theta equals. Now, honestly, this gets a little tricky to me, but recall it is a cofunction. So when you differentiate it, automatically there is a negative sign right out of the gate. But then it's negative of what exactly? Exactly. Cosine goes to sine negative. Derivative of sine will go to cosine positive. So this just becomes negative sine theta. The plus 1 is a constant, so that goes to 0. And that means we're done right here. The derivative is just negative sine theta. Now, if you differentiate this with product rule, it might take quite a little work to simplify down to that stage. Plus, it's just harder. So it's always good to think, can I simplify if I do something extra to this? Here, we definitely could. Any questions at the moment, folks? Okay, let's try out to one more that kind of goes like that. Then we'll do a slightly harder one with the quotient rule where there's no big tricks. We just have to sort of go through it and then simplify. So for part D, this one will be y equals. It starts with a parenthesis and goes secant x plus tangent x, multiplying the second group, secant x minus tangent x. And already, if you look at this, there's something funky going on with this problem, right? In the first parenthesis, it's secant plus tangent. But the second parenthesis, that's the conjugate, secant minus tangent. If you notice a conjugate pair, oftentimes a good strategy is just see what happens when you multiply this out and get a result. It's kind of like part C, where you might decide to try to hit it with product rule, but that work could be really substantial. And now this is a good time to use these properties down below. We're going to just multiply this out. A conjugate pair is almost challenging us to do that to see what we get. We'll try to use the formulas down here as we see them to simplify and then differentiate. So on this stage in green, nothing's happening except we're just simplifying the function. We'll multiply secant to secant. That's just going to be secant squared. Secant power 2x. Trig functions are extra special. We put the power 2's in strange places. It's often put here traditionally. If you put it, say, out here, it's not incorrect, but we would have to have parentheses for sure, so I know you're not talking about secant x squared, which would have a totally different meaning. It's part of the reason why this is a common notation. Put the power 2 right there, and there's less communications. Now, if we multiply here to here, that's negative secant tangent, but it cancels with this, positive secant tangent. So we have no middle term. We shouldn't expect it if it's a conjugate pair. Only thing last to do is multiply tangent with negative tangent. So we'll get minus tangent squared x. So we have secant squared minus tangent squared. If we were to differentiate this, that's two product rules. I mean, it doesn't look like it, but if you say secant squared x, that's secant x times secant x, really. And so differentiating secant squared with where we are right now in the course, it's a brand new product rule. So there was really no value in simplifying if we don't simplify even more, because there was already a product rule to start off this one. We made two product rules. It looks like this is harder on this line than it even started with. That's okay, we can keep on going. And now here's the next trick we might use. If you see a secant squared, or maybe a tangent squared, sine squared, or cosine squared, you want to use one of these three, the Pythagorean identities. So let's see here for secant squared, we could use, well, it's not even on here. That's okay, we can rebuild it for our property summary right here. I'm going to start with this and then pull out the identity. If it's true that sine squared, let me do this in orange. So if we have that sine squared of theta plus cosine squared of theta equals 1, what we could do to this equation is just divide the whole thing by, let's do something that will give us a secant squared back. If I divide by cosine right here and make it be power 2, 1 over cosine is secant, so 1 over cosine squared is secant squared. So we have the portion of the problem that we want to substitute out of there. We need to divide by cosine squared here and here. Oh geez, I'm pressing weird things on the pen. There we go. So finally, sine over cosine, is that tangent or cotangent? Good call. That one is the tangent function. So if it's squared over squared, that'll be tangent squared. Theta plus, here, just a glorified 1, equals 1 over cosine squared is the secant squared, theta. And now we have a way to eliminate that secant squared. We're just going to throw in tangent squared theta plus 1, doing a direct substitution from there to there. Does that make sense, folks, so far? Okay, my notes didn't quite give me what I wanted. I was hoping for more formulas right here. But if we pause for a moment and go back to these, I think it's got to be somewhere here. It'd be weird if they weren't. Where are those formulas? You know what? It might not be. I might have to update these notes just to give us a little bit more to work with. I was hoping for more Pythagorean identities than what I saw. I'll add a little bit more just so that we have these kind of identities as well. But once we're happy with that identity, we'll go y equals, in place of secant squared x, put in, well, it's going to be x because that's a variable, so tangent squared x. Plus 1 minus tangent squared x. And now there's a massive cancellation, right? The whole function is a constant function, y equals 1. And that's kind of unbelievable, but the promise is if you plot this in, say, Desmos, you should just get a constant function at height 1. There's lots of discontinuities whenever a secant has a 0 in the denominator or a tangent. But aside from those discontinuities, that's your whole function. And that means the answer would be dy dx, or y prime if you prefer. And it's going to be 0 on that whole thing. It's a wild problem because the calculus is right there and everything else was trigonometry and nothing else. So we're trying to review trig as well as develop the calculus as we're going at the same time. Well, any questions at all, folks, on getting through part D? Yeah. Only because it's a constant, yeah. Other questions or comments at the moment? Okay, So again, the kind of trick to this is definitely look before you leap. And if you just get stuck, say right here where the red dot is, secant squared x minus tangent x, sure, I'm missing some stuff that I like to have in my review notes, but you could always do this. Just open up any browser, click on or type in trig, identities, and almost like guaranteed, you're going to get probably what you wanted to start right off. The first thing in Google is probably what you want. And the identities I was going for that weren't on those notes, let's put them on our notes. They put them here, well, that's the identity here, but there's more. I'll just have to find a better set of identities, but it's good to know at least that's there. Let's take a screenshot of that at least. So that's how we got through that problem right there. Other questions or comments at the moment? Okay, let's try one more and then we'll switch gears to a different sort of problem. So this was part D. So for part E, let's try this next. So part E, I've got y equals, it'll be a sine. Looks like we're doing thetas again. So sine theta in the numerator divided by 1 minus cosine theta in the denominator. This one doesn't look too bad, but it's actually kind of the worst one in the set. Anyone see what would make this one more nasty than all the rest, potentially? Sorry, say again. It's not necessarily about the conjugate on this one, but there's something else that makes it just a little bit rather unpleasant compared to the rest. Yeah, go ahead. Exactly. This one's going to simplify a tremendous amount. So we're going to need loads of trigonometric identities to go through it. And it's strange because when we did these problems here, say to start out, there was no simplification. This one was product rule, no simplification. On C and D, we simplified first, and our derivatives required no simplifications after. This is one where you can't simplify it first, but when you take the derivative, it simplifies a ton. And sometimes that's kind of what happens with the quotient rule, unfortunately. This one's a quotient rule with one function divided by another. And so a lot of extra stuff can go into this one. So let's give this a try. This will be dy, d theta, we have to say this time, because the independent variable is theta. When we go to write this out, again, let me put the negative sign in the middle because I'm so used to putting pluses. I like product rule better. Then two sets of parentheses on either side of that negative sign. Let me get those primes in. Put a yellow here just to emphasize that's where those go. And the denominator to power 2. So that's our setup every time we use quotient rule. Now, numerator, if you have the numerator memorized to go to this location and this location, you're in really great shape. Because that leaves the denominator for everything else. So 1 minus cosine theta here, here, and here. So that's how we start this off. It just kind of becomes a slog. We'll get through this one. And as we solve this, think of this as kind of a trigonometry review in its own right as well. Let's put this on a new page just to be careful. Okay, I think that's a good spot to scroll. Now, going down the line, here's our next equality. First thing we have to do is differentiate sine. It's not so bad, we get cosine right back. So cosine theta here. Copy all this, 1 minus cosine theta. Minus in the middle, copy your sine theta. And finally, differentiate this one. And let's see what you would have to write down here once you differentiate. Exactly. There's an extra negative sign right here. And again, that's kind of what trips me up. There's constant flipping of the negative signs one side to the other. It gets worse once we start to integrate. So always be careful with those negative signs. It's a co-function, so it becomes negative sine theta canceling with that negative. So if all you wrote down was sine theta, good call. I'm going to put here negative of negative sine theta, just to show in the notes what happens with the cancellation there. So this negative came from right here, and that negative came from differentiating cosine theta, giving us the negative sine theta. Easy to miss those cancellations. There's really 3 negative signs here we're tracking, but does that make sense so far? Awesome. Then down the denominator, typically when you're solving and simplifying, there's usually no call to expand this. This is one of those cases where if you did expand 1 minus cosine theta to power 2, it kind of hides how it simplifies. So I'm going to leave it in its factored form with the hope that part of that will cancel. So 1 minus cosine theta down below, still to power 2. Now there's nothing more for it except we have to crank this out in this form. There's going to be things that combine, so there's definitely like terms. This will turn into cosine theta. Then when I distribute here to here, this will be minus cosine squared theta. Then that's handled. Finally, there's 3 negative signs. So overall, this is still negative. Then it's sine theta times sine theta for sine squared. Then down below, just 1 minus cosine squared theta squared. And honestly, if you left it in this form, I'm not going to be super picky about these. Yeah, go ahead.
How do you turn cosine theta into cosine squared theta?
This one right here.
I'm here from the top bit, the first part is this bottom parts. In the original denominator, it was 1 minus cosine theta squared.
Oh, that was my mistake right there. That should have been a direct copy. Should just be 1 minus cosine, 1 minus cosine to right here, just a 1 minus cosine. Thanks for spotting that. Other questions at the moment? Exactly, good call there. It's really this identity, right? It's just kind of hidden. If you see anything that goes cosine and sine squared and sine squared, oftentimes that's going to simplify. And the kind of thought on it is, let me write just off on the margin, minus cosine squared theta minus sine squared theta. You could factor out the negative one, leaving cosine squared theta plus sine squared theta. But now this is the world's best identity in trigonometry. Like you said, that's just a 1. The whole thing becomes negative 1. Absolutely, yes. And in this case, it depends on how we're going to do that though, because if we did use this identity, say 1 minus cosine, or hang on, 1 minus cosine theta, as it stands, it's not quite one of these because I don't have a power 2 right here. Are you saying like after you FOIL it all out?
No, I'm thinking.
Gotcha. I did accidentally put a power 2 here where I ought not have. I think I might have mixed up some of the visualization on this. But does that make sense with that question so far? Gotcha. Other questions or comments at the moment? Okay, well, we're getting through it. So far, the numerator, we have really just a glorified negative 1. Does that make sense to folks on how this all was hiding a negative 1? Okay, so take all of this. We're going to throw in a negative 1. And really it was just this Pythagorean identity here, the sine squared plus cosine squared, resulting in 1. Now we have a huge cancellation. This is just cosine theta minus 1 in the numerator, divide by 1 minus cosine. Oh, I almost did that again. Let me fix this. Cosine theta squared out here. Now, if it stands right here, it still simplifies, right? You can factor out a negative 1 from the numerator. If you did that, let's get some space. It'd become negative cosine theta plus 1 minus cosine theta squared. So all I did is factor out a negative from the top. So I flipped positive cosine to negative cosine. negative 1 down to positive 1 here. So the numerator is really 1 minus cosine theta, canceling with 1 minus cosine theta below. And so our whole thing is negative 1 over 1 minus cosine theta after we do that cancellation. Visually, the cancellation goes like this. That whole thing is gone. And that turns into a power of 1 instead of 2. So I just draw parentheses, and that's what we get. This one, again, is definitely kind of a nasty one. If you stop, say, right here, I probably would give full credit to that. But it's interesting to see how these do simplify, and there'll be times when we really need to if we're solving, say, a larger problem. If this was just one step of an applied situation, for example. But that's kind of the worst case for the derivatives you're going to see there for these notes. Any questions or comments at the moment? Okay, I said it's the worst case, but I'd say anything that might involve this can be tricky. So I have one more problem that does use the unit circle. You notice that all we're really doing is differentiating and getting a function back. But a problem that will make us evaluate the results could look like, say, this one right here. So here's our next example. Just for a point of reference, this one's also a homework question. I think it's towards the later part of the set. You'll recognize it when you see it, because it really just looks odd, right? It says the function is f of t, so the independent variable is t already. That's a little confusing. It's ordinary cosecant t, and this is saying take the second derivative of f with respect to t, and then evaluate it at pi over 3. So it's like a load of steps. It's really a 3-step kind of problem. But let's work this through and see what we get. Very first thing we need to do is just differentiate it. The Leibniz notation is not required, but it's good to practice with it just to train our eyes on what is it's really saying. So I'll keep it in Leibniz and write df dt. We would call it df dx only if this was f of x equals cosecant x. And if it was f of theta equals cosecant theta, we would have written df d theta instead. But with this, it's just saying f prime really. So we take the derivative of the cosecant function. It's a co-function, so we get a negative sign. Cosecant and secant are weird. They bring that portion back as a factor. So it's going to give back cosecant of t, and then it multiplies cotangent t. So that's our step 1. We had to differentiate to get to the first derivative. But it says d2f, dt2. So now we differentiate that thing again to get to our second derivative. Does that make sense so far on the process? Okay, awesome. So let's go to second derivative of f with respect to t. Powers always look kind of weird on this. We're not saying t squared. We're just saying we took the derivative with respect to t both times. But when we go to differentiate that, there's another conundrum with this function. It's not the world's best function to differentiate, right? Anyone see the worst thing about it? Or what kind of rule that we just have to use?
Product rule?
Exactly. We don't have any recourse. This one has to be product rule, only because of the multiplication right here. But it's simplified in a way so that this is the better simplification to work with if you need second derivative. So I'll think of this as the first function, cotangent as the second function, and we're just getting used to a product rule, so I'll write out in this template form one more time. Derivative of the first, copy the second, plus copy the first, and take the derivative of the second. So there's our product rule laid out. Don't do as I did and make a mistake on the primes. It's good to put them in right away, just to remind yourself what's being differentiated, what's being copied. So we'll drop that in. Negative cosecant of t goes here and here. And the last cotangent t will go here and here. Really don't like t as a variable. It just looks weird when you go to write cotangent t. I'll put a parenthesis just to make it, at least to me, a little bit more readable. Then on the next stage, we just differentiate these all out. Derivative of cosecant is negative cosecant cotangent. So we have extra negative signs here. It's going to be positive cosecant cotangent. I'll start by writing it out this way. This negative sign copies. Derivative of this cosecant function becomes negative cosecant t. Cotangent t. So that's our first portion done. Copying cotangent right here. Then the plus sign, and actually I should have looked before I leave personally. Really, we could just simplify this by saying minus altogether cosecant t. And now we need a derivative of cotangent t. Well, we can start off by putting in a negative sign right here because it's a cofunction. And the trick with tangent and cotangent is tangent is giving you back secant squared. Cotangent, it's almost the same thing, except it's giving you cosecant squared with a negative sign. So derivative cotangent becomes negative cosecant squared of t. So finally, it's all in. We just want to simplify this because we have to work with it. We're going to d2f dt2 evaluate at pi over 3. The more we simplify this, the easier the next steps are going to be. So here's what I'll do in the next step. Nothing major. Let's maybe combine negative signs here. It's cosecant t times cotangent t. Negative signs also cancel here, and the cosecant function will be raised to power 3 now, since it's cosecant times cosecant squared. So plus cosecant squared of t. Now finally, we return to this. That's our last step. But how do folks feel about here? Does that derivative look okay to everyone? Oh, it should have been cube. Sorry, I think I said it, but failed to actually do it. There's no reason it should absolutely be that. So the cosecant power 1 to power 2 gives us a power 3 altogether. Bad time copying today. Thanks for the careful, sharp eyes with this, helping out, folks. I appreciate it. Other questions so far? Okay. So last thing to do is a function evaluation. It's going to be take our second derivative, d2f, dt2, evaluate it at pi over 2, or excuse me, pi over 3. So the whole thing is take this line and just throw in pi over 3. Cosecant pi over 3 times cotangent pi over 3 plus cosecant cubed of pi over 3. All that's left to do is evaluate each one of these. We need to get exact answers as well. So although the calculator is helpful for checking if we're on the right track, we need to get this down exactly. So this is the trigonometric review portion. Yeah, go ahead. Here to here? Dear, yeah, there definitely was a mistake here to here. That should have been cotangent to power 2 right here, which means right here as well. Dang, this one was kind of nasty. Thanks for spotting that. Other questions at the moment? Yeah.
How did you give her the negative that's multiplied by?
This one right here.
Oh, no, the second line.
Second line. This one.
No, one below us. The negative times negative CST.
Right over here.
Yeah.
Oh, these two just multiplied negative by negative, gave us a positive altogether.
Would you also multiply negative by those tangents? No.
Only if there was a plus sign separating them out, because then you'd use the distributive law. It would multiply 1 and then the next term. But these are all being multiplied. It's essentially a -1 times a -1. They just annihilate each other right away. Does that make sense there? Gotcha. But yeah, if there was a plus in the middle, then you'd had to distribute, flipping both of the signs in that case. Other questions at the moment? Okay, well, last thing to do is calculate these all out. And to do that, here's our good old unit circle diagram. Really, what I would be doing is, if this was an exam question, that's a nasty one. It probably wouldn't be, but if there's a question like this, where we have to evaluate, I'm really just thinking of this. You'd probably just grab it. Let's duplicate it here just so it's in context. We rotate by pi over 3, which is about 60 degrees. Then there's two values. one right here is exactly 1/2 for the x coordinate. And this value is √3/2 for the y coordinate. So that's basically our sine and cosine. If there's a cosecant function, then we can say cosecant pi/3. That's just a 1/sine. So this is 1/sine pi/3. Then, well, if we look at pi/3, that's this rotation up here. The sine value is √3/2. So that just goes in right down in the denominator as a √3/2. Then this is 1 over a fraction, so we can take the reciprocal and call it 2/√3. That's what's going to happen to all of the cosecants throughout this process. That look all right to folks on that trig evaluation here? Okay, and that was so fun, we just do it again. The other function that came up was cotangent. So let's write out here. Cotangent pi/3. That's the one that goes cosine divided by sine. So it's cosine pi/3 divided by sine at pi/3. Then we go and look it up. Cosine is 1/2. Sine is still √3/2. So we just input those values in that way. Does that make sense to folks on those trig evaluations here? Yeah, go ahead. It's not so much that, but if you wanted to, I'm less worried about radicals in the denominator, but you are welcome to rationalize if you'd like. You can multiply by √3/3 and get 2√3/3. And that'd be completely fine. But for me, it's kind of optional. I'm okay if you use it just in that format, 2/√3. But let's use this right here. 2√3/3 is slightly more convenient because, like you said, we've eliminated the radical in the denominator. Other questions so far? Okay, on this one, we have 1/2 multiplying 2/√3. So this just becomes 1/√3. I'll leave this one in this form just to emphasize I'm okay with a irrational denominator. You don't have to rationalize it. Finally, last thing, we put it all in. Cosecant at pi/3, we got the 2√3/3. So that quantity there. Cotangent pi/3 is 1/√3. Sorry, say again. We did use this version that was simplified too, but someone asked if we want to rationalize it, what would we do? So I multiplied by √3/√3 to get this quantity right here. Oh, for cotangent. Well, these twos right here would cancel once we're multiplying through. So it'd just be a 1/√3 on that one there. Other questions at the moment? Okay, looks like we're slightly over time. Sorry about that, folks. We're almost through it. We just have to put in, for a cosecant, it's 1/√3, once again, to power 3. Then from then on out, we'd want to simplify that whole thing. We're running a little bit low on time, so let me show you what, no, I didn't actually write it down. I did at one point, but I didn't put down the answer. Yeah, go ahead. Oh, yeah, that should have been the 2√3/3. So that was cosecant 2√3/3 for that one. Absolutely. Sorry about that. I must have been just getting mixed up on which ones I was grabbing. Other questions or comments at the moment? Okay. Well, you don't have to stay for the last part. What I'm going to do is continue to simplify this, but we're definitely on overtime. Sorry about that, folks. Other questions or comments before we call it a night? Okay, this one was definitely a little bit more nasty than normal, but it is a homework problem. So when you see this one on the homework, this is about how it's going to go. I think yours is more like a f of t equals secant instead of a cosecant. So this one was meant to support the homework as well. Well, any last questions at all, folks, before we call it a night? Okay, have a great night, everyone, and we'll be back to section 3.4 on Wednesday's class. I'll finish out the simplification here, but you definitely don't have to stand by and watch. It's a bit of just kind of arithmetic drudgery, I'd say.